ready to start? Multiple regression? Alright. Good. Take that as a yes. Okay, so let's do a quick review of that Excel printout that we looked at on page 425 last time. So that is pretty much everything we need to know about regression analysis that we learned last week. And that is a good setup for what we need to know for multiple regression, which we'll learn tonight. Multiple regression is just a pretty quick, just a basic expansion of simple regression. So if you remember from the example last week, we were looking at number of apps and number of downloads. Actually, we're looking at apps, we're looking at the number of websites they were linked to, and the number of downloads each of these websites had. So we looked at 4 points of data. We said, all right, here's an app, it was linked to this many websites, and it had this many downloads. Let's run a regression to see if there's a correlation between the number of websites an app is linked to and the number of downloads. So we put this information into Excel, and it spit out this stuff. This gave us a number of important things. One, it gave us a regression equation, which is our estimated number of downloads we would expect based on number of websites. Two, it gave us performance measures, which is how well does this sample data fit those, or how well does the regression line fit those 4 points of sample data. Three, this gave us what we call inferential statistics. What can we infer about every app everywhere? So, based on this regression equation, can we walk into some tech conference and say, I can guess how many downloads your app received if you just tell me how many websites you were linked to? Are we comfortable, are we confident in saying that? That's what inferential statistics tells us. So, first thing, what is the regression equation that Excel gave us? I'll start us off as downloads, loads, equals what? 440 plus 11 times sites. Fantastic. All right, that is our estimated regression equation. You tell me how many sites your app was linked to. I will tell you how many downloads I think your app received. So, in terms of performance measures, the question is, how well does this line fit the sample data? Well, we have 3 building blocks which tell us how well this sample line fits the sample data. Total variation, unexplained variation, and explained variation. So the total variation, that's the variation from the average number of downloads. These 4 apps have an average number of downloads. Of these 4 apps, some of them have more downloads than average, and some of them have less downloads than average. We now have a way of explaining why some have more and some have less. It's because we think the number of websites these apps are linked to. So the total variation, this is variation from average. All right, how much is there? Some of that can be explained, some of that is left unexplained. Our independent variable sites explains a percentage of that, a certain amount. Some of it is left unexplained. If we have a lot of explained and a very small amount of unexplained, we like this model. We say it's great. And we're going to give it strong performance measures. So we take these 3 building blocks and we put them into our 3 performance measures. The R squared, the R, and the standard error of the estimate. Can I get 3 volunteers to tell me what those 3 are and what they look like in this particular case? Let's start with the R squared. What is that? What's another word for it, another term for it? And what is it in this case?
The R squared is the regression line equation? No.
It's not the regression line equation. This is the regression line equation, and this
The sample intercept and the sample slope give us the regression line equation. It's the R, Roxanne.
The coefficient of differentiation.
Yeah, coefficient of determination is another word for it. What is it in your own words, Roxanne?
It is what's explained.
What's explained? Can you be more specific than that? That's definitely right, but
What can be explained, percentage of it explains the variation within the model. The percentage of variation is explained by the variation equation.
perfect. All right, the percentage of variation that can be explained by our regression equation. And what is it in this case?
69%.
Point, 691.
Yeah, so 69%. All right, so that sounds good. It's better than 59. It's not as good as 89, but we really don't have anything to compare it to just yet. So we'll keep that in the back of our head. 69.1% of the data can be explained with this regression equation. All right, the R, what is that? How do we calculate it? And what do we really love about this R performance measure? Winnie, yeah.
It's the correlation coefficient, and it tells us if the slope is negative or positive.
Yes, the correlation coefficient, it's simply the square root of R, and what we really love about it is it can be positive or negative. If there's a positive correlation, that's one thing. If there's a negative correlation, that tells us something completely different. What would it mean in this case if there was a negative correlation? Roxanne?
There's an inverse relationship.
Yeah, so what does that mean in your own words?
Okay, in my own words, an inverse relationship. If something goes up, the other,
It's a down.
Yeah, so tell me about sites and downloads.
so the sites and downloads, maybe the more sites we have, the less downloads.
Exactly, that's what an inverse relationship would be. The more sites you're linked to, the fewer downloads we would expect you to have. Maybe if you're linked to a whole bunch of sites, that means your website, your app is not really good, so you're just compensating by throwing it, it's like a spam, whatever type of situation. That could be a valid argument if that were the case. It's not in this particular case because we see a positive relationship. Okay, and the standard error of the estimate, what is that? How do we interpret that in this particular case? Christina? Standard error of the estimate. Go for it, Chris.
Measures dispersion of the data around the estimated regression.
Okay, dispersion of data around the estimated regression line. It is in fact the average distance of each data point from that regression line. And in this case, what is it? 116, but 116 what?
Downloads.
Yes, downloads. So 116 downloads. Each of these 4 data points are 116 away on average from the regression line. So that gives us some context. Like if we're trying to predict within 20, it's going to be hard for us to do that because we know that each data point is on average 116 downloads away. So if we're trying to predict within 200 or 300, we might have more confidence in that. All right, great. So we've got 3 performance measures. We looked at them. We evaluated how well this line fit the sample data. Next is inferential statistics. So can we walk into this tech conference and say that we have a regression equation that is going to mean something with the whole population of apps and linked websites? Can we walk up to those tech designers and say, hey, I bet I can predict how many downloads your app received? Do you think we can do that in this case based on this inferential data? Alright, so we found out at the end of the class last week that probably we wouldn't really be very comfortable doing that. Let's talk about why. This slope, 11, how do we interpret that slope of 11? Well, we know that for every one website your app is linked to, we would expect 11 more downloads to be downloaded 11 more times. Do we have a confidence interval for this slope of 11? Because this is just a sample estimate of 11. Can we get a confidence interval for that? Yeah, how do we get a confidence interval for that? Or can you tell me what it is? Either one.
want the answer or the equation?
You can either tell me the answer or you can tell me how we would get it, your choice.
Well, we said it was between 33.3756 and negative 11.3.
Yes, okay, so we think this is 11, that's our best guess for it, but our confidence interval is between what, negative 11 and 33?
Yeah.
Okay, so what do we not like about that confidence interval?
It's too wide.
It's too wide? I'm not sure, because it's only 40 apart, that's 40, what does 40
Oh,
mean?
that there's a zero in there?
Yes,
Yes.
that there's a 0 within this confidence interval. Okay, so what does it mean if the slope is 0? No correlation. You tell me how many websites your app is linked to, I have no ability to guess how many downloads you have. 0. So I'm gonna go research something else, and then I'll get back to you. But it gets worse than that. Not only could the correlation be 0, when I'm standing up presenting this model, if I were to try to do that, I would say, well, you know what, the correlation could be negative. It could be more websites, fewer downloads. It could also be 0, or it could be positive. More websites, more downloads. Please invest in my tech startup. Right? I do not know very much based on this confidence interval. Alright, and how we got that is we took 11, and we took plus or minus some number of standard errors. So for this confidence interval, we took 11 plus or minus some number of standard errors. And to get the standard error, do you remember we used the t-distribution?
4.303
Yeah, t-distribution with how many degrees of freedom?
minus
N minus 2 degrees of freedom. Alright, and then we multiplied that by the standard error, also known as the standard deviation of the sampling distribution of the sample slope. Okay, and what is the standard error in this case?
5.2.
Yep, Excel gives it to you at 5.2, fantastic, and it's going to come out with that confidence interval. Alright, now, and we did a hypothesis test also. Now, we don't technically need to do a hypothesis test, because we just did a confidence interval. That confidence interval includes 0, so we know that this is not going to pass a hypothesis test. It's going to be a fail to reject situation. We can't be positive we have anything substantial here. But let's just do that really quick to make sure we're fresh on it. So our null hypothesis is going to be that the true population slope, this is just the sample slope, true population slope equals 0. Alternative hypothesis is going to be the true population slope does not equal 0. If this equals 0, we have nothing valuable to share with anyone, basically. If this does not equal 0, we have some predictive ability. So we want to know if this sample evidence gives us overwhelming evidence to reject this and accept this. What do we mean by overwhelming evidence? Something less likely to happen than our significance level. Commonly, we'll pick a significance level of 5%. Alright, so let's set up our little rejection region stuff. This is the sampling distribution of the sample slope. If the null hypothesis is true, the true population slope equals 0. If we find something a little bit more than 0, a little bit less than 0, we're like, okay, that's fine. But if it's a lot more than 0, a lot less than 0, we're going to start talking about rejecting the null hypothesis. Alright, our significance level is 5%. How much data is in each of these tails? 2.5%. 2.5%. Rejection region here. We are now, we need our t critical values. Alright, we want to know how many standard errors we need to go to separate the upper 2.5% from everything else and the lower 2.5% from everything else. We use a t-distribution with n minus 2 degrees of freedom. What are our critical values, upper and lower?
4.303.
Yeah. Alright, so 4.303, I like it. It's 2 degrees of freedom because n is 4 minus 2 is 2. So you look on the t-distribution, go down to 2 degrees of freedom. Move your finger over to the 0.025 in either tail, and you see 4.303. We're ready now to get our test statistic. Our t-stat is our slope. We want to know how different that is from 0. Sample slope is 11. How different is that from 0? It's 11. So the real question is how many standard errors of difference that is. If that's like 5 standard errors of difference, that's a huge difference. If that's like 1 standard error of difference, not a big deal. What is the standard error, standard deviation of the sampling distribution of the sample slope?
5.2.
Right, yes, you all are on it today. What does this test statistic come out to?
2.116.
2.116. Let's plot it. Looks like it falls about right here.
Failed to
T
reject.
stat equals 2.116. And our decision?
Failed to reject.
Failed to reject. All right. Let's see. What is the last thing? What is the p-value of this test statistic? Again, p-value is if the null hypothesis is true, that there truly is no relationship, what would be the probability of this sample outcome? What is the p-value in this case? 1686. About 17%. So this outcome is 17% likely if there's truly no relationship in the real world. Now, 17%, I think we said last week that that was kind of unusual, but is it extremely unlikely? Not extremely unlikely. It's not enough for us to reject this and walk into that tech conference with confidence and say that we've got some predictive model that you should invest in. It's not extremely unusual, so we can't rule out the possibility there really is no correlation in the real world. And you see everything that we talked about pretty much on this Excel printout. So the t-stat of 2.116 is right there, is right here under t-stat. What's the p-value for a t-stat such as that? Well, it's 16.86%. Confidence intervals, negative 11.4 and 33.4. All right, we find that. And of course, standard error you already pointed out. Good. Any questions? Feeling okay on this? Yeah, all right. Well, good. I think you all are in great shape then for the next step, which is multiple regression. Okay, so quick review of class 7, which we just did. We'll do a quick intro of multiple regression. We'll talk about a problem that comes up with multiple regression a lot, multicollinearity. I'll explain what that means, explain how we need to be aware of it. And then we'll look at performance measures with multiple regression and the inference side of multiple regression. This is pretty similar to what we did last week. Performance measures is very similar with a few differentiating features. Inference is similar type of concept, except we'll add a couple of things. We will then need to learn this F-test. It's not too difficult, and I've kind of watered it down, knew this term, to just give you a general idea of what it is. And what it has to do with is this multicollinearity issue. There's a problem when we start interpreting results in multiple regression. It's that the independent variables could be related to each other. That's multicollinearity. I'll repeat that several times, don't worry. So what happens then, because of that, is the t-tests become less effective, become less reliable. We can't rely on t-tests and t-hypothesis testing as much as we can, so we need to learn a new test called the f-test. Last thing we'll go over is dummy variables. These are qualitative variables. So a website is a numeric quantitative variable, or number of sites. You tell me number of sites, 1, 2, 3, up to however many. Dummy variables are just qualitative yes or no questions. Is your app a game? Yes or no? Does your app have a credit card feature? Yes or no? And we'll find out how many more downloads we might expect just based on those what we'll call dummy variables. And I'll explain that, of course. All right. So, quick intro to multiple regression. Last week, we looked at simple regression, and we went over this example, and we said, if you increase your study time, decrease your study time, how would that correlate with your grade in statistics class? So that was the independent variable, study time. Study time was the independent variable. And the dependent variable was your grade in class. This week, we will add more independent variables. What could be some other independent variables that we might add?
Getting enough sleep.
Sleep, amount of sleep. Yes, probably an inverse relationship. No. Sleep, a direct relationship. More sleep would mean higher grade, probably. Yeah, that's a good one. What else?
That's work.
Work, amount of work. Yeah, probably an inverse relationship with that, right? More work would mean lower grade, maybe? What do you think? All right. Yes, Roxanne.
Less family responsibilities.
Family responsibilities. All right, on a scale of 1 to 10, what's your family responsibility? So more would probably mean lower grade. Good. What else?
You said statistical background last time?
Background. Good. Your experience prior to this class. All right, so those are all good independent variables. So what we will do this week is we'll throw those variables in the model, and we'll see if we can get a better predictive ability to your grade in this class. So that's what multiple regression does. And of course we would want to do that. We wouldn't want to just limit our predictive ability to one variable. One variable may explain a small percentage of the variation. So let's see if we can throw in more variables and explain more. So last week, say for example, we came up with this equation. For every 1 unit of increased study time, you would expect your grade to increase by 15.1 units. All right, and that is your predicted grade in statistics class. This week, we're going to add another variable. Let's say we still track study time, but this time we add experience in statistics prior to taking this class. So we get a different equation. And you'll notice that this variable 1, independent variable 1, the slope coefficient changes. And we will find that this is actually a more accurate slope coefficient. So for a 1 unit increase in study time, we would expect a 12.4 unit increase in grade. When we just did a simple regression, we were giving too much credit to study time. It turns out that once we control for your background in statistics, that it only has this much effect on your actual grade. So once we introduce other variables, we get more accurate slope coefficients. First advantage of multiple regression, more accurate slope coefficients. Second advantage, the R squared will increase. What is the R squared again? Yeah, and in your own words, what is that?
How confident you can say that your equation is correct, like your different variable explains
Percentage of the data you can explain.
Percentage of the variation that we can explain. You're on the inferential side of statistics, which is good, but this is percentage of the variation we can explain. The more, the better. So for this, we can only explain, say, 60% of the variation. Here, we can explain 72% of the variation. So closer we get to 100, the better, right? The R squared will always increase or stay the same when we add more variables. It will never go down. So you can keep throwing more and more independent variables into this model, and your R squared would only increase. Disadvantages. Extra work. So extra work you may not think is a problem when you just put the numbers into your equation or put it into Excel, but what it translates to is extra sources of error, extra data that you need to track, extra data that you need to be able to explain. It just makes your model more difficult. So if that variable is not adding anything useful, then that extra work, additional source of error, can be a problem. So you just need to be aware of that. The next and most important disadvantage we'll discuss tonight is multicollinearity. Sort of cut off here. You have to come up and look at it on the silver thing. That's what it said, the third one, multicollinearity. So what that means is these two independent variables are highly correlated to each other. So the amount of hours you spend on statistics and the background you had in statistics are highly correlated with each other. That's maybe not the best example of multicollinearity. Let's suppose this second independent variable was your interest level in the class on a scale of 1 to 10. So if you were highly interested in this class, you would probably be more likely to spend a lot of time studying. So those two variables highly correlated with each other. So the problem becomes, if they're highly correlated with each other, we can't really tell which one is actually having an effect on the dependent variable. Right? So if you're really interested in class, that means you study a lot, so that means you would have a high grade. Is it because you study a lot, or is it because you're highly interested in the class? We can't tell, because the independent variables are highly correlated with each other. So what we'll see if we were to run a t-test on these two slope coefficients is we might see very large standard errors, and we'd have very wide confidence intervals, which would possibly include negatives, and they would fail hypothesis tests. So we would look at these individually, or we'd look at these if we run a multiple regression, and we'd say, gosh, you know, the strength of this model really isn't that good. The reason that might be happening is because of multicollinearity, and it's because these two independent variables are highly correlated with each other. Does that make sense? Excel is not able to tell the true strength of either one because of the correlation they have with each other. Yes, Joe?
And is it because two variables have a similar correlation? Is it because adding the second one is like doubling the amount of influence? Does that make sense?
Yeah, you're kind of double counting.
Yeah, is
Yeah.
that what that means?
It's like you're double counting.
Yeah,
Yes, yes. All right, so what we need is we need a couple things. The first thing we need is an overall test to determine whether or not the regression equation as a whole is strong. And that's going to be our F-test. So I'll teach you that momentarily. So we'll run an F-test to determine if we have a strong regression equation, if there is strong predictive ability with that regression equation as a whole. And often you'll find with the F-test, yes, it is statistically significant, it passes a hypothesis test with flying colors, but then when you test the individual do individual t-tests for the coefficients, you're confused. You don't know which one is truly causing that. So you do a couple of different things. You can run the F-test, then you can try running each of them individually and say, you know what, I just want to go back to a simple regression with this one, or maybe I want to go back to a simple regression with this one, or maybe I'm going to keep them both, but I'm going to understand that there are things that I need to control for, monitor, not be too confident about. All right. So these next two slides just kind of sum up those discussions, why multiple regression and how multicollinearity fits into it. So multi-regression allows us to identify the effect of one variable while controlling for the effects of others. So last week we may have given study time too much importance. This week we're going to control for the effect of your previous background in statistics and really zero in on the accurate, the more truer cause of how much time you spend studying and how that relates to your grade. By taking into account the likelihood of shared or overlapping predictive ability, multiple regression can reduce the risk of assigning a greater degree of importance to a particular independent variable than is merited. This does lead to a problem, however. Multicollinearity is correlation among independent variables. When independent variables are highly correlated, it's not possible to determine the separate correlation of any particular independent variable with the dependent variable. So the independent variables are study time and previous experience. How much do each of them really relate to the dependent variable of grade? It's hard to tell when we put them both together because they're highly correlated with each other. So adding more variables will increase your R squared, which we talked about, but you'll lose an understanding of which variables have the best predictive ability. You risk assigning too much importance to any one variable. And your goal should be always to find the model that explains the most variation with the fewest amount of independent variables. And that doesn't necessarily have to be one independent variable. It could be 3 or 4 rather than 20. Any questions about those two concepts? Why multiple regression, how multicollinearity throws us a curveball, and we'll see how we address that with the F-test. Okay, so we talked last week about simple regression being a line of best fit on a simple scatter plot diagram. If we think of adding a second independent variable and a third and a fourth, we might think of multiple regression as a plane of best fit. If that helps intuitively think about it, that's a good way to intellectualize it. We will still come up with a regression equation, just like we did last week. No, there's a funny little symbol there. I don't know how that got there, I'm sorry, but this is y with a little bar over its head. Alright, that's the predicted value for the dependent variable. You still have a sample intercept plus sample slope 1 times coefficient 1 plus sample slope 2 coefficient 2, so on forever, however many independent variables we have. And we'll still ask the same question. Alright, this is the sample slope. What is the true population slope? This is the sample slope for coefficient 2. What is the true population slope for coefficient 2? Alright, so same way as last week, we'll get an estimated regression equation, and we will try to find the true population regression equation, and we will see how confident we are with our sample regression equation. Alright, so multiple regression connects a single dependent variable, 2 or more independent variables. We plot it on a plane of best fit. To find that plane of best fit, we still use the least squares method. We take the deviations from that plane of best fit, square them, add them together for all the data points, find a way to make that a little bit smaller if we can, then we've got a better regression equation. Each coefficient represents the change in y corresponding to a 1 unit change in x when all the other variables are held constant. Remember, we said we are going to hold the your background in statistics constant. We're going to control for that, and we're going to now determine the true effect of how much study time influences your grade. But first we have to control for how much background you had before you started this class. All right, so we're ready to look at an example. Suppose we work for this website, collegesports.com, and we want to predict win-loss records for basketball teams. So we are collecting data on basketball teams. We're collecting things like turnovers per game. We're collecting things like field goal percentage, rebounds, steals, all that kind of stuff. And we want to try to determine which of those as independent variables can predict the win-loss percentage as a dependent variable. So let's start by looking at two independent variables. Let's look at turnovers per game and let's look at field goal percentage. And we'll see if we can use these to predict a team's win-loss record. So we're going to take a simple random sample of 20 teams and we're going to construct a regression equation. We're going to decide if we like that regression equation. And that's going to give us an estimate of the win-loss record of any team. Now let's go over some basketball basics here. What is field goal percentage? Can someone tell us?
Quantity made over quantity total.
Yeah, that's right, that's right. I've never heard a basketball player say it quite like that. Quantity made, it's just how, it's just how, your accuracy. Yeah, so you shoot the ball 10 times, if you make it in the basket 9 times, your field goal percentage is 90%. So higher is better, right? So we would expect you have a higher field goal percentage, a better win-loss record. Turnovers per game, what's a turnover?
When you have the ball on offense and you lose the ball.
Yes, you lose the ball, all right? So you're dribbling the ball, you're gonna go down and shoot a basket, and someone just takes it away from you. All right, it's completely legitimate, all right? They take it and they score with it. So turnovers are bad. So the more turnovers you have per game, you would expect a lower win-loss record. All right, so let's put these data into Excel, and let's run a regression. Ready to do it? All right, so let's run that regression, and let's get an estimated regression equation based on field goal percentage, turnovers per game, to predict win-loss record. All right, so let's run that regression and see what Excel comes out with. Okay, so take a look at this printout in Excel. Tell me what you know about this regression analysis. I want to know, of course, what the regression equation is. Then I want to know what the performance measures are. And then I want to know what you can tell me about the inferential statistics. Just take some time, check it out, talk to your neighbor, bounce some ideas off of each other. I need to know, definitely need to know those 3 things.
What were the 3 things again?
Regression equation, performance, what is the word here? It's performance
Measures, you said?
measures. Sorry about that. Performance measures and inferential statistics.
So that's the equation.
I guess so.
You could think I don't know what they do. Estimated one last question, so it's gonna be, go back to
Yeah, that's like good.
let's
Which side?
Like, it's split, these are the same two things, so I'm saying that like.
Those are 20 different teams. This is the you don't need to run the regression, but it's you can if you want. Right. It's if you run the regression, it'll look like that. I mean, it'd be great if you could do it from the regression. But all you really need to do right now is find what three things, Roxanne?
The regression equation, the performance measures, and the inferential stats.
Thank you. Yes.
Oh, because they have multiple variables. Oh, the way you did it last week was the reference, that's so long, right? So then you have multiple variables.
Those are X's, so you're gonna need another X. So the X range, you would just, so, and you can, yeah, and you would select as the X range this whole thing.
The whole thing.
Yep. Exactly.
However many times.
Exactly, and I was telling Kelsey that it's good you're doing that, but you don't have to do it right now, just concentrate on the interpretation. Unless you can do it fast.
No.
You do it. Yeah, you don't have to actually do the regression right now unless you can do it fast, in which case I'd be impressed. But we really just want the interpretation.
Okay.
Go ahead.
Go to Excel. Checks tonight.
Okay, well,
Vendors.
I hope you don't get held up on your way. Okay. They're just checks.
Yeah.
Brad, do
Google
that.
Excel. Split it out.
The regression equation.
I thought you were just meditating to better absorb. You hear me?
Yeah, I knew it was in that. Yeah, I really could, it's been all day.
Good.
But I think
Good job, I like that discussion. You got my feeling? See that, you got a blank piece of paper. Should we start discussing this? Do you need a couple more minutes? Should we do it? No? Yep. All right. What is our regression equation? I'll start it off for us. Win-loss percentage equals negative 50? 474 plus 3.606 times what?
X1.
Yeah, field goal percentage. All right, plus negative plus negative 4. What's an easier way of saying plus negative 4? Minus 4.
0.069.
30
No, 069.
4069?
Yeah.
9 times.
Turnover.
Excellent. Excellent. So, for a 1% increase in field goal percentage, say we shoot 34%. If we could get that up to 35%, how much would we expect our win-loss percentage to increase or decrease? Yeah, we would expect it to increase 3.6% for every 1 unit increase in field goal percentage. Alright, so we could go to shooting practice, do some meditation, some, I don't know, some wrist exercises, right? You know, make your wrist stronger so you can shoot more effectively. Alright, for every 1 unit we could probably increase, we might be able to increase our win-loss percentage by that much. Turnovers per game. Alright, so if we can practice protecting the ball, good passes, good crisp movement, if we can decrease our turnovers per game by 1, alright, say our average turnovers per game is 9, suppose we can get that down to 8, how much would we expect our win-loss percentage to change? Yep, it would go down by 4%. Alright, so if we could, yeah. So if we could decrease it, it would actually go up by 4%, right? If we get decreased turnovers per game, it would go up by 4%. Alright, that's the regression equation. First question, performance measures. How well does this regression equation fit the sample data? Tell me what you know. Start with the R square. What is that? What is that in this case? How does that make you feel?
0.5,
Okay, what is that?
which is like 53
53% what? Yes.
for the R square.
Yeah, for the R square. What is the R square?
The percentage of variance. Is that the same thing as the difference here?
Coefficient of determining.
Okay, I like how effective your equation is.
Explaining your,
You said it's the percentage of variation that is being explained by the regression.
That is correct, right. It's the percentage of variation that is explained by the regression. So in this case, how much is it? Yep, 53% of the variation is explained. So, okay, that's better than 30%, not as good as 80%. We'll just keep that in the back of our head. So, we now have a model that explains 52% of the variation. If you come up with a model that explains 72% of the variation, then you say, forget this model, I want the model that explains 72% of the variation, right? Alright, so that's really all we can say about it for right now. Alright, and then the R, multiple R, this is just the square root of R squared. Now, remember we really love this R, the correlation coefficient, because it can be positive or negative and tell us whether the relationship is positive or negative. In multiple regression, we lose that with the R squared because we have multiple independent variables, either which could be positive or negative. So this will always be positive. But if we want to know if there's a positive or negative relationship, all we need to do is just look at the slope coefficients. This is positive relationship, this is inverse relationship. Alright, and third performance measure, who can tell us about the standard error? Remind us what that is and what is it in this case?
How close the points are from the average?
Okay, is that right? Is she right or wrong? So how close the points are from the average?
Average regression line. Sorry, regression plane in this case.
Yeah, so she said average, and that's an easy mistake to make because we've talked a lot about the variation from the average. But you're right the second time, it's actually what?
The regression plane.
Yeah, how close the points are from the regression line or regression plane.
Okay,
All right,
so don't
and-
say average.
And in this case, it is 11.8. What 11.8 what? What are the units?
Points. Like wins? Oh, yes.
Winning percentage. Okay, so of these 20 teams, on average, they are 11.8 percentage points away from this line of best fit, plane of best fit. So, that's kind of gives us a scale of how close we can measure, how accurate our estimate might be. All right, very good. Let's do some confidence intervals. Alright, how about this confidence interval for field goal percentage? I said a minute ago, if we increase field goal percentage by 1 unit, I'd expect win-loss percentage to go up by 3.6. Can you give me a confidence interval for this? Yeah, 95% confidence interval, sorry.
0.6988.
Yep, so just give me the interpretation. Okay, say I'm 95% confident.
That the field goal percentage will affect the win percentage. Lies between 0.6988 and 6.514.
Perfect, perfect. So he's reading from right here. This is the lower bound of the confidence interval, upper bound of the confidence interval. And we start, so the really accurate way to say that is I'm 95% confident that the true population slope is between this and this. He's throwing in cause and effect, and we'd be careful a little bit about doing that. We're going to start doing that a little bit more this week because that's ultimately what we're trying to determine. All right, what will cause a higher win-loss percentage? We want to be careful about how we do that, but we ultimately want to get there. So we'll start throwing that in a little bit more, so thank you, Tanya. All right, so do we like that confidence interval? Based on that, are we feeling like we can go to the NCAA tournament and start pitching this model to teams? You know, maybe start using it to make some money gambling? I don't know. Yeah, how are we feeling about this based just on that confidence interval? What do we like about it?
And it's both positive.
Yes, it does not include 0. Yeah, if it included 0, that would be a problem, but it does not include 0, so we're liking it. All right, fantastic. How about the confidence interval for the turnovers per game? Someone want to just do the interpretation for confidence interval turnovers per game?
I'm 95% confident that the true population slope for turnovers per game is between negative 8.11 and negative 0.02.
Perfect, perfect. So what do you like about that confidence interval?
Doesn't cross 0 again.
Yeah, again, it doesn't cross 0. Excellent, excellent. So based just on this alone, do you think these two independent variables are going to pass hypothesis tests? Meaning, are we going to be able to reject the null hypothesis and say, yes, these are statistically significant? Yes, absolutely. Absolutely. If you were to plot them, you would get t-stats of 2.61 and negative 2.12. You know they would both pass based on the confidence intervals. What would be the p-values of these sample outcomes? Again, p-value means, I'll actually go ahead and write it up so we're clear here. So we're going to look at a hypothesis test, all right, for each slope coefficient. Null hypothesis, true population equals 0. Alternative hypothesis, true population does not equal 0. And we want to know, can we reject the null hypothesis? All right, and we're going to get a t-stat, which is going to help us make that decision. All right, and the t-stat of the first one is 2.6. The t-stat of the second one is negative 2.12. So tell me the p-values for these two t-stats. Again, the p-value is if the null is true, if there's really no relationship statistically between these two variables and the independent variable, then what is the likelihood of this sample outcome? All right, so tell me about the p-values. All right, so I need 2 volunteers, 1 for field goal percentage, 1 for turnovers per game.
0.01 and 0.04.
Okay, 0 point, Yeah, okay, so who wants to explain field goal percentage p-value? Wendy? No, alright. Wendy gave us the numbers, we now need an interpretation. Kelsey?
Is it 1.8%? Like, is that number turned into a percentage?
Yeah.
Okay, so like 1.8% that you'll get this range again, or you,
Okay, what does p-value mean?
like how likely is that to happen again?
If the null is true.
If the null is true,
If there's no relationship
that there's no relationship,
between the independent and the dependent.
yeah, that the slope is 0, then what?
There's no relationship between the
The
independent and
likelihood of
dependent.
getting that sample,
Yeah. What is the likelihood of this sample outcome? What is the likelihood of seeing this slope? Let's look at it that way. If there is truly no relationship, if the null hypothesis is true. So what's the likelihood of seeing this slope if there is really no relationship between field goal percentage and win-loss percentage? What's the percentage likelihood of that happening? 1.8%. Alright, so do we consider that very unlikely? Yeah, so what do we do with that information? Because it's very unlikely.
reject the null.
We reject the null hypothesis. Alright, should we do that? Should we work that out?
How would you interpret it, like how do you say it for the p-value?
Yeah, alright, let's just do it out. Alright, so I'm throwing a lot of information at you quickly, so we're forgetting what we know. So, null hypothesis is the slope coefficient for field goal percentage equals 0. Alternative hypothesis, the true population slope field goal percentage does not equal 0. Alright? We're going to assume this unless we have overwhelming evidence to the contrary. If we do, we're going to reject it and assume that it does not equal 0. So what does it mean if the true population slope equals 0 again?
No relation.
No relationship between what and what,
The
Joanne?
independent and the dependent variable.
In this case, which is?
The field goal percentage and the win-loss.
Yeah. So if the slope is 0, there's no relationship between those two. Wait, just tell me, what do you think? Is that true? Is there a relationship between field goal percentage and win-loss?
Yes.
Yeah, there probably is, right? I mean, you can't win games unless you actually make baskets. So there probably is a relationship between those. But we're going to need overwhelming evidence before we say yes, there is. What do we mean by overwhelming evidence? Something less likely to happen than 5%. Alright, so let's draw our sampling distribution of the sample slope for samples of field goal percentage. If the null hypothesis is true, that the true population slope does equal 0, then that's what it would look like. If it's a little bit more than 0, a little bit less than 0, no big deal. A lot more than 0, a lot less than 0, we start to think about rejecting this and saying, yes, there's a relationship. So what are our critical values?
2.5.
Okay, now actually I didn't tell you something about critical values yet. We're going to use a t-distribution again, except we're going to use a t-distribution with, last week we did n minus 2, this week we're going to do n minus k minus 1. K is number of independent variables.
Oh.
That's not too bad, right? Alright, so if n equals 2, or no, n equals 20, k is number of independent variables equals 2. Degrees of freedom
7.
equals 20 minus 2 minus 1. 17. Alright, and how much area, if our significance level is 5%, is in each of these little tails?